Should we get started, everybody? All right. OK, before we get going, tell me a little about who I'm talking to here. How many people are using Kubernetes in their day job? Wow, that's so different than last year. Cool. How many of you have used a service mesh as part of that? That's a bunch of you. How many are using Linkerd as part of that? Good, good, good. How many people have been to Seattle before? Cool. We were all at the last. Who was at the last conference? Let me put it that way. At the last Seattle KubeCon. Nobody. One, two. OK, three. Yep, OK, we got a couple, but you're all newbies. I wasn't here either, though, so it's OK. All right. So my name is Oliver Gould. These are my dogs, Draymond and Bo. My background's in production operations. I out of school, spent some time at school, and then went to Yahoo. Yahoo, for those of you who remember what that was a really large internet directory. And it was really like 20 different companies that have been acquired over 15 years, all in some crazy bastardized infrastructure across the globe. All the systems were in local time, which is crazy, and FreeBSD 2 to FreeBSD 9, and then we started introducing Linux. But that's all to say, I learned that the internet is run with duct tape. That there's not this really well-oiled machine out there, that the perfect internet exists, that we're lucky DNS works at all. And then from there, I went to Twitter, and I was really lucky to start when I was kind of the second programmer in ops, and I got a lot of good projects. We replaced the Ganglionado system with a custom-built observability thing, which is based on Cassandra. Prometheus is in that same vein, and I prefer using that to what we built. And went on to the traffic team and worked on a bunch of Finagle stuff, which led me to the problems we wanted to solve in Linkerd. And then I started a company with William, who some of you just saw, in 2015. And we've been, for the last couple of years, working on Linkerd. And I've been kind of the creator of that and one of the primary driving forces behind that, though we do have a team at Buoyant and across the globe working on this. I have a GitHub account. And again, these are my very lovely dogs. That's from this morning, actually. So what is this talk? What is a deep dive? I have 25 minutes or so to do a deep dive. I will go as deep as I can in that. But what I'm not going to do is explain to you what a service mesh is or why you want to use it or any of that stuff. There's a lot of other talks here that can tell you that, I hope. I'm going to tell you about Linkerd and the decisions we've been made and kind of the journey that we've been that got us here and where we're going forward. So we launched Linkerd at KubeCon EU in 2016. That one on the left there. Then about a year later, we gave it to the CNCF. And that year was really getting our first set of production users, making them successful, helping them be successful. And once we had really proven out that Linkerd was a valuable thing that people wanted to use, we got more serious about the open source community and donated it to the CNCF as a kind of investment to say that this is not a proprietary thing that Buoyant owns and is doing. We want to give this to the community so that you don't feel locked into Linkerd. And in that time, we've had plenty of users. These are a lot of big fancy logos, but we also have a lot of small little logos that aren't up here that are using this to power small e-commerce shops and banks and what have you. And it's a pretty active project. We have a lot of real-world users solving problems with it. For who was at KubeCon in Austin last year? Who saw my keynote demo where I got up and tried to do so we launched this project called Conduit then. And Conduit was kind of a departure from Linkerd. And we didn't port forward any of the features of Linkerd 1. We ditched dtabs and the whole config language and everything associated with Linkerd 1 to start new. And that's why we didn't want to call it Linkerd. We wanted to call it something else so it could fail. And we spent about 9 months working on that, as long as most valuable things take to build, like babies. And then we birthed Linkerd 2. And that was really, in that 9 months, was to find production users, people who had production problems that Conduit could solve and help them be successful. And once we proved it out, that this is something really valuable, we gave it back to the CNCF and merged it in as Linkerd 2, and we think this is the future of the project. And the real hypothesis that the shift going from Linkerd 1 to Linkerd 2 is really on these 3 tenets. One being lightweight, and we've called ourselves the ultralight service mesh, and that's for a reason. And lightweight, both in terms of resources, the proxy takes less than 10 megs. It's quite small. But also lightweight in terms of complexity. I don't want you to have to go learn something to get value out of a service mesh. I have an aside here that service mesh is a pattern, like the actor model. You can build all sorts of different applications with the actor model, and they all have different focuses and strengths and weaknesses. With a service mesh, we don't think you have to go learn some big policy or compliance system to go get started. We want something that's really lightweight conceptually that you can reason about yourself at 3 a.m. without calling me. And a big part of that is not having magic. If there's a feature that you don't understand, that's magic. And if you're on call for that, that might be great for a demo. Right at the conference, we have all these magic features, which everyone knows and ahs at. But when you go deploy that, and a month later, and you don't know my phone number, and you wake up in an incident, how are you going to figure out what's going on? Well, if you're in a cloud provider, maybe you can call your cloud SREs. But a lot of the customers we have need us to be able to solve these problems themselves, and without us, hopefully. Though we do, we have a bunch of support relationships, and those are great. But what we've learned from that is that we need to give you the ammunition. And in a service mesh, because this is the first hop into a network, the service mesh is guilty until proven innocent. And that's how it should be. So Linkerd needs a ship with an alibi. It needs to, you need to be able to introspect and say, did you mess up? Or is this the network? Or is it something else? And that's really informed our strategy in terms of feature development. So if you look at our feature list compared to others, you'll say, wow, Linkerd doesn't do nearly as much. And that's for a reason. We're not adding features to Linkerd that you can't debug. Full stop. That is the goal of Linkerd, that if you run this thing, you have to be able to debug it yourself. And that brings us to the third point, which is tactical, not strategic. Strategic things are things you have to get the whole company on board with. You got to get all the architects in the room around the whiteboard and have a consortium to decide what is the one true service mesh for Beyond Corp or whatever you're at. We don't think that has to be the case. Our Linkerd is designed to be tactical, and that means incremental. So you can use it to solve specific problems today. You can install it today, and it will help you. And it will grow with you. And you can install to one service. You don't have to install to a whole cluster, let alone your whole company. And then you can expand from there. And it doesn't get more complex as you add things. The value actually gets magnified as you add it to more services. And that is really our goal here. So here's the big kind of architecture diagram of how it works. We have and actually this is already at a date. This was before the 2.1 release last week. The destination service and proxy API have been collapsed to one service. So we're quite small now. We have a web and CLI that uses an interface, which is in a Linkerd namespace, or maybe your own namespace, depending. We ship with a couple small microservices there. And we also bundle Prometheus and Grafana. And that's not to replace your Prometheus or Grafana. And in fact, we don't want to do any long-term storage of time series here at all. We want this to be something that lets you ask questions of the proxies now. People, when they go to production, tend to either configure their own Prometheuses to scrape from ours or to scrape from the proxies directly. We don't prevent any of that. But this is meant, again, you install this bundle, and it's immediately useful. You don't have to go build other things or configure dashboards or do any of that work. And all of that, modulo some of the web stuff, is written in Go. We also have React and some other technologies in there. And the choice for that is to use client Go. I've, in Linkerd 1, written a Kubernetes client in Scala. And almost, well, I don't know what percentage, but large percentages of the bugs in Linkerd with Kubernetes have been related to that API client. And changes, subtle changes in the versions between releases and things like that are quite hard to debug. And so our grand genius idea was, well, client Go is perfect, right? Everyone who's, if you're using Kubernetes, like what is in kubectl is client Go. So we should be using that. And we have been, and it's been pretty successful, though it is by no means a silver bullet. Hold on one second, please. Then in the data plane, we've elected to write our own proxy in Rust. Anyone here write Rust? Anyone here want to write Rust? Cool, yep. Next year, there'll be way more hands, I promise. Rust is, anyone here not know what Rust is? I thought so. OK, yeah, so Rust is a modern programming language. It's memory safe. It has a whole bunch of affordances that I'll go into at the end of this if we have time. But our bet is that we don't want to be writing native code in C or C++ in the year of our Lord 2019. We want to be using modern tools that allow us to be way more effective at doing that job. Does this all make sense so far? Great. So I want to start and go through a quick walkthrough of how we get bootstrapped with Linkerd. I'm just going to hit a bunch of technical notes as quickly as I can, and then hopefully get to questions at the end if we have time. So the problem is you have an application, and we have to add a proxy to your application. How do we do that? Well, we have this Linkerd inject logic. On the left hand here, we have a bunch of uninjected, we have a Kubernetes manifest with a bunch of deploys and services and daemon sets and whatever, and it just has apps and nothing special. We then transform it through the magic of Unix pipes through Linkerd inject, and that turns into a new manifest with a proxy init container and a proxy container in the resources that deserve those things. And as we heard in the last talk, Ivan just developed an experimental feature to replace that Linkerd inject command line tool with a mutating webhook that will do this in the server, in the cluster directly. And here we can see that there's a whole bunch of options that you can configure when you're doing an injection. And this is really around how do we configure the proxy init container. The proxy init container is really there just to configure IP tables rules. So all the traffic going into the pod goes through the proxy, and all the TCP traffic going out of the proxy going out of the pod goes through the proxy. This requires netadmin capabilities, which is kind of a deficiency right now. But we have a whole bunch of interest on replacing that, likely with a CNI plugin. So that's some upcoming work there. Again, so this adds two containers to each pod resource described in manifest. An init container, which manages IP tables rules, and a proxy container, which is this Rust application that deals with transmitting and proxying TCP connections. So I want to do a quick dive through the life of request to kind of help you give some context of how the proxy is built and what it does. And so we're going to be focusing on this data flow, going through the proxy. And actually, I'm going to talk mostly about the outbound side, so going from the application out of the pod to another service or an external service. And there's just very slightly different logic on the inbound side. But the outbound side is a little bit more complex, so I want to cover that. A lot of hand-drawn slides that I definitely did not do in my hotel room this morning. So when we accept a connection, we just get something from the Kubernetes network, right? And that's coming in through the IP tables rules that we configured with the inject command and the init container. And what that gives us is we have a TCP server that accepts connections, and we use the socket option, original dest, to determine where that traffic was initially headed. So if you're sending traffic to google.com, or better yet, twitter.com, as you go through the pod, it's going to hit the proxy, and we now are no longer sending it the destination is the proxy. So we have to ask the kernel, where was this socket going before we intercepted it? And so we maintain that information as we make our routing decisions below. We then have this TLS decoding layer. And this is just watching files on disk for certs. And so in the demo we saw from Sebastian earlier, they have a CA client that's just refreshing certs in the local file system. The proxy just picks those up. And right now, at least, it'll only decrypt connections from other proxies. So if you have TLS connections that are going through the proxy, and a proxy did not send that, it'll just forward it through as normal TCP, as if nothing ever happened. And so our philosophy there is to kind of fail open. We don't want to have a big mandatory thing where we'll break existing applications. We want this to be able to layer in and add value wherever it can. And well, if we can't decrypt your traffic, then we can't give you stats about that in a meaningful way, but at least we're not breaking it. Then we have a kind of pluggable layer in there called the accept stack. Right now, that's really for transport layer metrics. But you can imagine that we could also add policy there, like whitelist, blacklist for IPs, et cetera. And then we do protocol detection. And so there's no, unlike Linkerd 1 where you have routers configured for individual protocols, now we're in the TCP stream and we're listening for data. And so we wait for some data from the client, and when we get that, excuse me, we know immediately whether that was an HTTP 1 request, because we can read the first few bytes and know it's HTTP 1, or we know it's an HTTP 2 special magic header, and we can turn it into H2, or otherwise we say, hey, I don't know, it's TCP. Anyone see any problems with that? Come on. Someone guess. What's the problem with that? All right. Anyone know how the MySQL protocol works? Yes. So MySQL, when a client connects to it, it sends nothing. It's quiet. And it waits for the server to send some data before it does anything, which makes a proxy like this, we can't do protocol detection for those things. And so one of the deficiencies right now, if we go back to the inject command, we see that we have these skip ports here. And that's a necessary evil right now for us to allow you to talk to MySQL through the proxy without us doing protocol detection that breaks it. And so if we don't do TCP forwarding, we shunt it all off to the HTTP routing stack. So with HTTP routing, we take both, we decode through either H1 or H2, depending on the protocol we detected. But everything else in the proxy then just gets merged in. And the only difference between them in our logic is the HTTP version on the request metadata. And you'll see why that plays in later. So HTTP 1 comes in, we handle it through the same stack as HTTP 2. Again, unlike Linkerd 1. And then that immediately goes through the destination router. And this is really fundamental to how, again, very different from Linkerd 1 to how the Linkerd 2 proxy does routing. And so we use the authority headers specified in the URI. So if it's H2, there's an authority header. If it's an HTTP 1, we look in either the resource for the authority or look at the host header. And if you're in some weird HTTP 1.0 situation, we'll use that original dest address from that socket option as the destination to route to. And then we have this canonicalization logic. And here is what, because names can go through the proxy and be relative, you can have foo and foo.ns and foo.ns@service.cluster.local all going through the proxy. We want to be able to normalize that into some predictable name that we can hang policy off of. And so we use DNS for that. And so we and this is nice, so any DNS policy you've set in your pod actually will just apply natively here, because we're using the same DNS server. And so we do the lookup and say, OK, if the header foo came in, the authority foo came in, I'll do a resolution for foo, and whatever fully qualified domain name resolved there, which will be foo.service.cluster.local, if that's a local service in my namespace, we'll use that for the purposes of routing discovery later on. Make sense? You're asleep or yes? OK, and so the next step, and this is a new feature in 2.1, came out last week. This has been a big part of my last few months is working on this stuff. And so once we get that canonicalized name, now we can actually go to the control plane, the proxy API service, and say, well, what are the policies for this name? foo.service.cluster.local or google.com or twitter.com or anything. We can go to the control plane and say, do I have policies for that? And right now, policies are basically, you can think of it like OpenAPI, Swagger spec type things. And that allows us to hydrate metrics here and response classification. Response classification being, how do I know whether this request should be considered a success or failure for the purposes of success rate calculation or retries? We don't have retries yet, but that will be in 2.2 coming out towards the end of January. Once we go through that route stack, and there's many route stacks, so you download a bunch of these from the control plane. That's all gRPC watches there. All of the APIs with the control plane are gRPC. All those policies are stored as one CRD in the Kubernetes API. And then we go to a load balancer. And that load balancer is going to use that same name, that authority that we've canonicalized, to resolve to a set of IP addresses. And we use the Kubernetes API for that rather than DNS. So we try to use the Kubernetes API for that rather than DNS so that we can get a whole bunch of Kubernetes metadata. And so what the proxy API service does here is says, well, I'll do a lookup for these sets of endpoints, but I'll also, once I get those IPs, I'll say, this IP is actually in this namespace, in this deploy, in this replica set. et cetera. And we can actually take all of those labels from Kubernetes, throw them back through that response, and now we hydrate all the metrics that come through that path, get all of those labels annotated. So when you go to Prometheus, you actually have all of your Kubernetes resources in the labels and dimensions. So you can ask questions like, what is the success rate in this namespace? And that just falls out of the Prometheus model. There's nothing special we have to do other than add these labels from the proxy API. The proxy itself knows nothing about Kubernetes at this point. It's just dealing with names and labels and very generic things. So we get that, and we also get a little bit of extra metadata there, including, is there a proxy installed on the other end of this, on the other pod here? If there's a proxy installed there, well, we might be able to do TLS upgrading. We can also do protocol upgrading, which I'll get to in a second. If none of that exists, though, and we don't necessarily go to the proxy API for all domains, it's only whitelisted for service.cluster.local right now. That gets configurable. But if that's not there, then we'll fall back to DNS, again, to not break anything. And we'll do load balancing based on that as well, which is still better than kubeproxy will do. We'll do request-aware load balancing. And so that means we measure the latencies for each request the proxy sends to each endpoint. We measure the latency from the time the request is sent until the first byte comes back. It's not the headers, the first byte in the payload. And that lets us actually get really good request-aware load balancing using the PQM algorithm, which is very similar to what's in Linkerd 1, though I kind of think we may have improved on it a little bit. But so that, again, we can resolve names through DNS, get a set of IPs back, and load balance over them, even to non-Kubernetes resources. OK, and then for each endpoint that we get back from that thing, we have another set of policies. And so the endpoint is the IP, whether we can H2 upgrade, whether there's TLS, and again, that set of metric labels. And within there, we have another TLS watching system, and that's if this endpoint supports the proxy TLS, and there are certificate credentials local, then we will, the rest of the below this stack will be aware of that TLS configuration. Within that is a metric system. And so we're recording request totals, response totals, latencies, et cetera, for every request. And then we have this concept of tap. And tap, here we have a server that comes from, the proxy is serving a gRPC port, so it's a gRPC server. And that control plane will connect into the proxy and say, I want 100 requests that match these criteria. And that might be to this authority, or with this path, or this method, or some combination thereof, or everything but this method, or but this destination. And so this gives us the ability to do kind of ad hoc introspection of traffic as it's running. Right now, this is really limited to the metadata about the routing. But as William said before, at the point after the last release, the proxy is at a place where adding payloads and arbitrary data there is not really technically difficult. It's mostly a UX problem that I really want to solve in the next few months, or I really want you to help me solve in the next few months. Maybe? OK. Anyway, from there, we also we get this information back from the cluster, from the Kubernetes API, or from the proxy API, sorry, that tells us whether there's a proxy running on the other side. If there is a proxy on the other side, well, we can do HTTP2 upgrading only in that proxy, only to proxy. So your application doesn't have to speak HTTP2. We will have one multiplex connection between proxies, which in a TLS world gives you a lot of amortization of costs. So you're not reestablishing connections for every request. We can just trunk this all safely and efficiently. And then from there, we were to say, based on all these decisions we've made, is this go on an H1 client or an H2 client? So we can really do protocol upgrading and downgrading with some caveats just through the proxy configuration. OK, and now for the fun part of the talk. I want to talk a little bit briefly about our use of Rust and how and why, and hopefully be able to get some questions at the end. So number one, strong typing. This might look like a bunch of gobbledygook, and when I got started with Rust, this really hurt my head. But now I've learned to love this. This is a beautiful explanation of a contract. And this is actually the metrics service that we're using. And it is totally type safe and memory safe and all these things, and generic over the types of modules underneath, the services underneath it. And so if anyone's written Finagle before, Georgie, this might look really familiar, though a little bit different. And this is super powerful. I can't really explain how powerful this is, But the point here is we're able to build generic modules. So the metrics module, we can test totally independently of the proxy. In fact, we use it in multiple places in the proxy. So this module is used in the routing layer, where we have these per route metrics, and also in the endpoints layer. And if we want to add other scopes of metrics, we can just not copy and paste the code, instantiate new instances of this module elsewhere. And this type of modularity is super powerful when building modular correct systems. You want these contracts that mean that changes between modules can affect each other, or that those changes have to be documented well. And the other kind of really crazy thing about Rust is the resource acquisition is initialization kind of mantra, RAII. And what that means is that we can rely on the LLVM to manage references between modules. And so for instance, when we do service discovery through the proxy, we have a service that's doing the lookup. And that actually goes and sends some requests to the API, and we'll have a stream open that's watching the request to the API. And if this service is to be deleted, say it falls out of the cache and we don't need it anymore, it idle times out, well, all of that can just be garbage collected without having to do a real garbage collector. And so just by dropping the references in the listener, everything else can just be dropped for free if you're doing this correctly. And so here is in the metric system where when the request body, so when the request is done, when the reader of the response, when the reader of the response is done processing it, it drops the object. And LLVM will say, OK, when this object drops, we have to record latency here. So this is kind of similar to finalizers and other languages, but Rust's primitives here and assurances and like the model here is really compelling. And I know I'm not doing it justice here, but I encourage you all, if you're interested in like low-level system or mid-level system programming, to go give Rust a spin. It's been really good, and we've built a lot of kind of core libraries here. So everything from the HB2 implementation is a native implementation in Rust that we wrote, as is the gRPC implementation, which so now we have contributors from Google working on that. And the load balancer we've written there, and the router we've written there, and the circuit breaking is being added there. And so there's actually a big framework of components and libraries that you can go use to build your own proxies if you want to. But I hope you go build libraries there to help us make Linkerd better. That'd be even better. But the point is, there's a whole ecosystem that underlies Linkerd that is being used at other notable companies like Amazon and Dropbox. They're building on the same stack that Linkerd 2 is built on. OK. And so coming up, we're really going to continue to invest in service profiles. This is a new concept that was kind of covered in the last session. But service profiles are the way that we will hang policy off of services. And that starts with just route definitions of being able to describe endpoints and different API structures. But with that, the next step will be setting retries and latency SLOs on those routes. So the uploading a photo endpoint is going to have a different retry policy and a different timeout policy than the download a tweet endpoint, right? And we have to be able to describe those things. So the descriptions just formed in 2.1, and the policies will start to land following that, including rate limiting, and I think probably canaries will happen before rate limiting. But another big initiative right now, as I mentioned, is dropping the netadmin requirement so that you don't have to grant all of your pods netadmin capabilities, and hopefully just have that as a cluster owner. Automatic injection is ready. People are using it in prod, as we know. Thanks, Will and Ivan. And I expect there's a few more kind of UI tweaks we want to do before we call it stable. But I'd expect that in the January timeframe, I hope, Ivan. Yeah, but come get involved and help us make that good. Again, the diagnostics are really core and key to what we're doing here, and if it has to be debuggable. And one of the problems, I think, in the proxy is the logs are kind of a mess, just because we have a whole bunch of libraries all logging different things, and getting the full fire hose of that can be quite hard to debug. And so we're actually building into the core networking libraries all the way down as far low as we can, a tracing system to do structured logging. And so that allows us to subscribe to events and actually know the structure. So I can say, for requests to this pod, show me all the logs. and I can get really structured data about just that stream and that connection without having all the other things. And we'll be able to turn that on and off at runtime from the control plane so that you can debug this for yourself, or you can give us really good bug reports. Another thing I think that's pretty easy, and I would encourage a contributor to get involved here, is that since we're using Prometheus and we have a control plane, and Prometheus alerts are just Prometheus queries, what we're really looking to do is build a library of alerts that we should have on the control plane itself or on common aspects of the data plane, so that if you want to point alert manager at our Prometheus instance, you can get alerts for free about at least the health of the control plane itself, if you don't have that already. But we think it should be pretty easy to have out-of-the-box things like that of, is Linkerd healthy? Again, so that we come with our own alibi, so you don't have to do the murder mystery thing. And one of the things which is a little bit of a science project that we're starting to work on is deterministic resource consumption. And what I mean by that is I want you as a service owner to really have a trade-off between latency and memory consumption. And that is the trade-off, especially when you're dealing with highly concurrent workloads. You can throw more memory at the proxy, and it'll be able to do way more buffering and way more concurrent work, and that's OK, but that comes at the cost of memory, right? But we can manage latency. Or you can say, well, I don't want this proxy to take more than 10 megs, and let the latency be damned, right? We want to have back pressure there in a really good way. And so we have a bunch of the fundamentals are moving there. Things like having a channel implementation. If you really want to get the details, we have a multi-producer, single consumer channel implementation. Right now, it allocates more than it should, and so we're really stripping allocations out of that so we can be very predictable in terms of these things. But I think we'll get to the point where there is an easy mathematical formula to determine the resource consumption of a proxy based on a latency target. And I hope we can do that this year. OK, finally, Adam up here told me I have to tell you all that we're hiring. But we're working on a bunch of really cool stuff. We're working on the Rust proxy. We're hiring for the control plane and the UI. We just want people who really want to work on this stuff. So if you really want to work on this stuff, come talk to this guy up here afterwards. We have a website with a bunch of docs. I actually saw some of you reading the docs during the last talk. That's pretty cool. And we have a Slack where you can come chat with us. And there's, again, a pretty active community there of people willing to help who don't all work at Buoyant. And then we have a bunch of GitHub repos. And so the Linkerd org is where Linkerd 1, the Linkerd 2, and the Linkerd 2 proxy are housed. Hyperion is the HTTP library, or Hyper is the HTTP library. That's kind of the Rust de facto HTTP library. The author of that works at Buoyant, and we're really tightly integrating that into Linkerd. Linkerd is built on Hyper and Tokyo. Tokyo is asynchronous networking library in Rust. You can think of it similar to Netty, you Java folks, or I don't know what the other equivalents are, libev, I guess. And Tower is our Finagle replacement in Rust. And so Tower is a service abstraction. This is where the load balancer lives. This is where the retrials live. This is where the rate limiters live. And so this is a bunch of reusable components that you can go build web services or proxies or whatever you want. And all of this, this is all an investment that Buoyant has made in the open source community on the core primitives under Linkerd 2 that, again, are used in way more places than Linkerd 2 right now, like the Dropbox client, I believe. Desktop client. Finally, I have a Twitter account. It's pretty bad. Don't follow it. Anyway, thank you very much. I'm happy to answer questions if I still have time. I have no idea what time it is. I have 5 minutes for questions, and thank you. Just switch down. And Adam here will dispatch the mic to those with questions.
Which one you want?
You pick them. I'll knock them down.
Where's hands?
Yeah. Sorry.
Are there any scaling considerations, the knobs we need to twist or whatever?
Yes. Are there any scaling considerations? Right now, the proxy is not actually multi-core. I should have said this. Right? We only have one core for proxying and an admin core. And so you will hit some limit there, especially with low memory, in terms of how much concurrency you can get through a single proxy. There's some work going on right now. I think, again, Q1 timeframe, we'll be able to scale that up. And once we can scale it up, we'll start to tackle ingress use cases and things like that. Other than that, please find some bugs for me.
Any way to know if we're going to hit those limit? Any way to know if we're going to hit those limits before we try it?
That's a good question. I think it would be a question of concurrency in terms of the number of requests being sent through the proxy at any one time. Not open streams, but concurrency. We can talk after. I think there's some easy redline testing stuff we could build or work on there that would make it easier to answer. But it's not there immediately yet.
I was just curious if you saw any value in decoupling the control plane from the data plane so that you could, for instance, use the Linkerd control plane with Envoy or the Istio control plane with the Linkerd data plane? Or if you think they're always kind of like be bundled together?
Yeah, so I think that'd be okay, right? I think if other proxies wanted to implement our APIs, that'd be fine. We didn't really want to participate in the place where we're going to have to go standardize APIs to innovate. We're a startup and not IBM. And so we want to be able to iterate really quickly, and that means that we can make changes in the proxy and in the control plane in the same version and just make those together. And so we like that coupling, but they are decoupled in that there's just a gRPC interface between the control plane and proxy, so it's not really that hard to go write a new control plane for the proxy that maybe is an adapter to those other control planes. That's just not really a priority for what I'm doing right now. But good question, thank you.
Is there a multi-cluster story for cross-cluster service mesh?
That's a great question. So not yet, but federation is in general a big problem we want to tackle, and that should have been on that last slide. And so because we support a single namespace install, where a controller can be installed in a single namespace or for just a subset of a cluster, the federation between namespaces is the same thing as federation between clusters to some degree. And so our plans there are to really nail the identity model and make sure we get the mutual TLS story nailed. And then once we have that, we'll expand outside the cluster. But yeah, definitely a 2019 thing, and we have an issue open on it. Definitely comment on it or give it a thumbs up or whatever that lets us know you care about it. I think there's a question up here, Adam. Yeah. Yeah. Come on, hurry up, Adam.
Hey, so I have two questions.
Oh yeah, go for it.
Cool. So the first one is to do with service-to-service authentication. So what's available in Linkerd for that?
So right now, Linkerd out of the box has this optional TLS module where it's not doing mutual TLS, but it's doing the server-side certificates, and that's automatically provisioned, so you don't have to worry about it or anything like that. There was a demo in the last talk where Step is building another CA that can do this as well, and that will be the mutual TLS story, I think.
Okay.
None of the authorization stuff in terms of ACLs is really there yet, but our identity first, and then we can start to solve those higher order problems.
Gotcha. And on that, is there a way to kind of perhaps plug in other authentication strategies?
That's a really good question. Please open an issue on the Linkerd repo.
Okay.
They're like, no, this is other people asked me at this conference about that.
Yeah.
And I just want these forums where other people can go add to that.
Cool.
So it's not there yet, but if the community wants it and people will use it if we build it, it'll get built.
Cool. Okay. Awesome. So the last question is to do with
Three questions. Okay, sorry.
It's to do with protocols, right? So earlier you were saying that you essentially have a mechanism that allows you to kind of detect what protocol you're talking. So then you use the appropriate one.
Yep.
But I suppose at the moment it's TCP and HTTP, I think you said.
Yeah, basically.
Right. Is there any intention or any intention to add anything beyond that? So you mentioned MySQL, for example, right? So I'm familiar with other proxies that not even preemptively, they specifically say that a particular port is going to speak, let's say, MySQL, right? So you can do a lot of cool stuff if you know stuff ahead of time.
Yep.
Is there any intention to kind of put this into Linkerd?
Yes, with a caveat. So in a Kubernetes-like environment or a distributed environment, port reservations are not really a real thing, and so you can't someone was like, oh, InfluxDB runs an 8086 and its server speaks first, so you should whitelist that. And I'm like, well, our proxy API runs on that port too, so what do you want me to do? But I definitely think that we'll we do have a set of default well-known protocols that we will just pass through as TCP without configuration today. And as far as being aware of those other protocols, it really depends on how that protocol works. Some protocols really work well with middlemen, like HTTP. Other protocols like MySQL, less so, because they're very stateful in terms of the protocol. And so if there are specific protocols that you'd like to get, and really what we get there is the stats and the routing, right? And so if there's like a Redis would probably be a fairly simple one to add as far as I understand of the protocol. And so those are not hard to add once we have a codec. And so it's really just a matter of building the client codec for those things. So if you want to write some Rust.
Cool, OK. Should I finish?
Oh, you have four, yeah, there you go.
OK, cool.
Yeah.
So specifically, the reason why I'm asking about protocols is because it kind of ties into what I was asking in the earlier question about authentication, right? So you have something like MySQL, which clearly has like an authentication strategy, which like you're not going to do mutual TLS. You have to provide credentials. So then I was wondering if there's like an integration point in Linkerd where you can essentially have a mechanism to say, well, I just want Linkerd to kind of do the handshake for me and then shuttle bytes after, right? Yeah,
it's a pretty interesting use case. It's definitely not there yet, but I would be pretty interested to have that conversation.
Cool, OK.
And yeah, that's all I got for that. Yeah, thank you. All right. If we're not getting kicked out, I'll entertain one more, and then we got to go.
Hey, so quick question. This is more about Go versus Rust, but not at a technical level, more community level. So have you found that switching to Rust or starting the proxy in Rust, in terms of like open source contributors, like have you found that they might have had like a harder time just coming up with Rust and the ramp up time for that? Rust I know has gotten better about that, especially in 2018, but just curious about
and the very fact that we've had to build all of these libraries in Rust is kind of a testament to the fact that the ecosystem's not there. And I think for a lot of people who want to go build web frameworks, it's just really just not there yet, and that's okay. We have had where we have seen community interaction in Rust is the community of like serious production users who want to build things, like systems people at Amazon and Dropbox, et cetera, MIT. We have a community there that's really working on Tower in Tokyo, et cetera, less than the proxy. So we have not had a lot of external contribution in the proxy. And that's actually been OK, because it's been changing really rapidly. I expect in 2019, I really want that to change. So yeah, it's been way easier for people to get in and contribute to the Go side. But part of our investment in Rust is to raise the bar so everyone else can get there too. But we're definitely believe that like Rust is a good bet. I have no reservations about that bet. All right, I will be Buoyant has a booth downstairs. Come say hi, and we're happy to talk. Thanks again.